There we go. Now let's share the screen and get into solutions and solubility. Okay. But before we do, I do need to start off the lecture with a bad science joke. A bear falls in the water. It says, "Help, help, I'm dissolving." The other bear on land says, "But bears are insoluble." And the bear, thank you, thank you. That's easy for you to say. You're not polar. We'll talk about like dissolves like. And so this could be a little misleading because non-polar things can also dissolve, but they have to dissolve in non-polar solvents. Whereas presumably this is water, which is polar. So like dissolves like. Now, that brings us to what a solution is. A solution is a homogeneous mixture. Homogeneous meaning it's essentially the same throughout that entire solvent. So it's a homogeneous mixture of two or more pure substances. Now, what is a solvent? A solvent is what the solute dissolves into. Okay, so when we talk about solutions, we have a solute and we have a solvent. The solute dissolves and spreads uniformly or homogeneously throughout that solvent. Okay, and there are all different types of solutions. The air we breathe is a solution of different gases. Soft drinks are a solution of carbon dioxide and water. That's what I have right here. I make my own soda by just pumping carbon dioxide into water, and it gives it that nice bubbly effervescence. Things like rubbing alcohol, that's isopropanol. It's a certain amount of alcohol dissolved in water. And if you go to the store, you can buy different percents, right? 70%, 95% rubbing alcohol, 50%. Those things are going to be just how much alcohol is dissolved in water to get a certain concentration. Salt water, obviously, we've talked about that recently. It's sodium chloride breaking apart into the water. And then it doesn't have to be gas or liquids. You can have solutions that are solids, right? So brass is an alloy, a mixture of two different metals, zinc and copper. And those come together to form a solid solution. Okay. Now, what facilitates solutions? We know from last week that things are held together by intermolecular forces, right? London dispersion forces, hydrogen bonds, dipole-dipole, ion dipole, right? And so in order for something to dissolve, the intermolecular forces holding the solute together have to relinquish. Likewise, the intermolecular forces holding the solvent together must also relinquish. Okay, and so the hydrogen bonding in the water and the ionic bonding in the sodium chloride needs to relinquish to now liberate these ions so that they can then, the negative ions bind with the positive end of the water and the positive ions bind with the negative end of the water. Okay. If, for instance, an ionic salt like sodium chloride is soluble in water, what that means is that the ion dipole interactions that occur between that ion and the water have to overcome the intermolecular forces that are holding that into a crystal. What kind of crystal, right? a lattice crystal, which we did in our ICA this week and we talked about last week, right? So what keeps those individual unit cells together into a larger crystal must be overcome by the ensuing ion dipole interactions that will form. And again, this has to be under these conditions of like dissolves like. Okay, polar dissolves polar, non-polar dissolves non-polar, right? That's why oil doesn't mix in water, because oil is non-polar, water is polar, so they separate out. Okay, now sometimes you will have interactions that the solvent solute interaction isn't as strong as the actual solute interaction. Okay, that doesn't mean it won't dissolve. You can still get a solution forming if the energy to essentially go uphill and break those interactions in that solvent or that solute, if the energy isn't so demanding to make that impossible. Okay. And that is why, again, like dissolves like. Now, how does a solution form? Well, there are three major steps. One is that the solute particles have to separate, right? They have to break their intermolecular forces. The solvent has to separate their intermolecular forces, and the new interactions have to occur between the solute and the solvent. And all of these steps are going to have with it some kind of enthalpy change. Okay. So getting back, it's all coming back to enthalpy yet again. Okay. And the total energy to break things apart, and then the total energy to put it into a solution. And the relationship between those two energies of breaking down and then forming new bond or new attractions is going to yield an overall state of enthalpy. And depending on the value of that enthalpy, the reaction will be endothermic or exothermic. Okay. So this is really just piggybacking on everything we've been learning so far in Chem 102. Okay. Let's talk about a little bit of the characteristics of solutions. They're, as I said, homogeneous, right? So they're evenly distributed throughout the solvent, right? It's usually the same physical state, okay? So again, if we're talking about air, it's going to be a solution of gases, okay? If we talk about taking a solid sodium chloride and dissolving it in a liquid water, then that solution is now going to be liquid and liquid. If we're talking about the alloy of zinc and copper, it's going to be solid, solid. Okay, so the physical state of the solution is going to be the same between the solvent and the solute. And then the components that make up these solutions are going to be consistent, going to be homogeneous, all the way down to the molecular scale. Okay, so the molecules, the atoms that make up those molecules, the ions, if it's an ionic solution, it's all going to be evenly dispersed. Okay. And then finally, the dissolved solute shouldn't separate out from the solvent. Okay. Unless you start removing solvent, right? If you start evaporating out your solvent, eventually they'll separate out, especially with things like salt water, right? The salt doesn't evaporate. You'll end up with the the salt back at the bottom of the cup if you were to have salt water. And if you add more solute than the solvent can interact with, then you'll start getting precipitate down at the bottom, right? But if you have a solution that has dissolved and you haven't put in a lot of temperature to make it super saturated, which we'll talk about later, then it shouldn't separate once it's formed a solution and it's a closed solution. You're not changing the conditions of it. Okay. Now, this brings us to, again, the relationship of energy, because all of this comes down to energy, right? The energy that keeps the solids together, the energy that keeps the liquids together, the energy that that doesn't keep the gases together, per se. Energy is the theme of this class, right? So when we talk about energy in terms of a solution, we call it solvation. That's the energy that is consumed or used to overcome those interactions between the solutes and the solvents. Okay. Now, it can be, as I said, an endothermic process, or it can be an exothermic process. And that just depends on the particular types of solutes and solvents and their overall enthalpy. Okay. So let's say if we have energy that is consumed to overcome these interactions, that's going to be endothermic, right? Because it's consumed. But if it's released, then it's going to be exothermic, right? And so if it's a positive value, it's endothermic. If it's a negative value, it's exothermic. And it's an overall stepwise process, okay? And each step, we look at the enthalpy values and we add them up, and then we get total enthalpy, and that will determine whether or not it's endo or exothermic, okay? And if it turns out that the enthalpy of the solution is negative, then what? The solution is releasing heat, the temperature increases. And this is a way to look at it in the stepwise manner, okay? So let's say we have, down here, we have our solute in green, and I'm sorry, our solvent in green and our solute in red, okay? And we're going to have to look at the enthalpy change over time. As the enthalpy change goes up, eventually you're going to put enough energy into the system to start breaking apart the interactions of the solvent and the solute. Once that happens, we have to compare it to the enthalpy of the mixture, the enthalpy, that's the energy that's going on when the solute and the solvent are mixing together, okay? And depending on, again, how those compare, it'll be endo or exothermic, okay? In this case, it's taking more energy here to separate than it does to mix. So you have a net endothermic process. But if we look at the next slide here, it's not there. Where did it go? Huh, I thought I put in an exothermic process. Well, if it's exothermic, then it's going to be the opposite. Let me draw here. Sorry, guys. An exothermic would mean that the energy that goes into the mix is going to go all the way down to here, okay? And that the energy required to separate them would be let's say starting right here, okay? So this distance is greater than this distance here. And so you have an overall net, sorry, terrible drawing, a net exothermic process. Okay. Uh-oh. Why did you stop sharing? Sorry about that. Let's see, chat. Would this be a state function? Yes, essentially this is a state function. We're talking about enthalpy, so it's still a state function, right? It doesn't matter the steps involved in between. What matters is where we end up. Good question. Good to clarify. Okay. So now that we know that, we can calculate these different enthalpies to determine if it's exo or endothermic. Okay. And this is called heat of hydration. What's the heat of hydration? The heat of hydration is the heat that is released or emitted when 1 mole of a gaseous solute is dissolved in water. Okay. So the heat of hydration is the heat that is released when 1 mole of solute dissolves in water. Okay. Think of this in terms of ions, really. Okay. And so we can figure out the heat of solution by subtracting the lattice energy from the enthalpy of hydration. Okay. And what does that mean? Well, the lattice energy is the energy keeping that solid together in that crystal. Okay. So let me do some annotation here. So the change in enthalpy of the solute, right? Because that's what's dissolving in the solvent. That is going to be equal to a negative lattice energy, or the enthalpy of the energy required to keep that solid together. And let's say in the case of potassium fluoride, that's going to be 821 kilojoules per mole. Right? And those are the units because it's still enthalpy. We're still using the enthalpy. Only it's the enthalpy in relationship of this solid. So if we say that the energy to keep that together is 821 kilojoules per mole, and that the enthalpy of hydration, the enthalpy required to break that up and bring it into solution, is a negative 819 kilojoules per mole, then we put those two together, and the enthalpy of the solution, right, this right here, turns out to be, in this case, 2 kilojoules per mole. Okay. It's the difference of the energy keeping it as a solid and the energy keeping it or driving it into a solution. All right. So, different types of solutions. Saturated solution is when the solvent cannot form attractions with any more solute at a particular temperature. Okay. So what happens when you heat up salt water, right? Or let's say you want to make salt water. You put a pot on the stove and you increase the heat. You're going to dissolve it more quickly, right? Because you're going to just speed up the rate of this reaction. But a higher temperature can also increase the degree of saturation, and that will make something super saturated. And we'll get to that in just a minute. But when we talk about saturated in this context, at a given temperature, it's the condition by which you cannot add any more solute. It'll just precipitate down to the bottom of the jar. Okay. So you have your water and you're adding salt and you're stirring and it's dissolving and you don't see the salt. And then at some point you start seeing the salt, it's not dissolving. That's because you've saturated the solution. Unsaturated, of course, is when you can still add solute. You have not used up all of the parts of the solvent molecules. They can still form attractions with the solute. Okay. And the overall condition of this is that the solute's concentration, all right, the concentration of, if we're talking about salt water, sodium chloride to H2O, is going to be less than the solubility. Pretty straightforward, right? Now, if something is supersaturated, as I said, the solvent holds more solute than is normally possible at that temperature. Okay. And this is done by increasing the temperature, right? So you're adding energy in there. And so you're letting these things happen because of the increased energy that you've put into the system. But they're not stable, right? As soon as the energy is dissipated, then it will form back into a just regular saturated solution, and any additional solute is going to precipitate out. Okay. And this can be done by, again, lowering the temperature or adding a seed crystal, right? That unit cell, if you will, kind of, that seed crystal will cause these other like molecules to then bind and form really, and depending on what you use, really cool structures. I think this is sodium acetate, which is a really common chemistry demo. You put sodium acetate in solution, you supersaturate it, and then you can scratch, just kind of, scratch the side or etch the side of the container, and it will cause a disturbance. And then you'll start seeing these beautiful crystals just grow before your very eyes. I was watching a chemist. So I watched this YouTube video where they were interviewing this very prominent chemist who had never watched the Breaking Bad series. And they finally convinced him to watch the first episode to see what his take was on the chemistry and how legit it was. And he was talking about one issue where one of the guys was smoking a cigarette in the RV when they were making the methamphetamine, and it brought him back to when he was a student in chemistry, and they were making solutions and trying to get crystals, and one of his partners was not getting any crystal formation, and the professor was walking around the lab, and the chemist now is like probably in his 60s or 70s. So back then smoking was much more prevalent, and smoking in the lab was not necessarily frowned upon. And so the professor walked up and took his cigarette and flicked the ash into the solution, and that served as the seed crystal, and all of a sudden all these crystals formed. So not something that would happen anymore, but a relic of the past.
Hey, so I wanted to ask a quick question about that. Is when it's forming into a crystal, it's like destabilizing, or it's losing, it's falling out of solution. Is there an energy associated with that can be measured?
Sure. So again, to have it supersaturated, you have to typically add in more energy to drive it. So to drive it past that difference between the lattice energy and the hydration energy. Okay. And so once you start decreasing that, once you bring that energy back down to these values, for instance, then you should start seeing crystallization form. Okay. And so you could directly computationally. Yes. Sorry, I got a chat. Martin Polyakov. He's a guy who he's in these periodic table videos. So he does these YouTube videos where they talk randomly about basically any and every element on the periodic table. I recommend checking them out. But yeah, so if you were to see this crystallize, there would be a certain energy release that is no longer, so once that energy is gone, now it's not driving it into that super saturated state. And again, remember, like dissolves like. Okay, so polar substances dissolve in polar solvents, polar solutes in polar solvents, non-polar solutes in non-polar solvents. Okay, and so when we look at different alcohols, right, we can assign different solubility factors to them in their relationship to water. Okay. And a lot of that has to do with the number of OH groups it has on it. Okay. So if you think about these more complex alcohols as we get down the list, it's harder and harder for them to dissolve in water. Okay. All of them, well, most of them, anything that is ethanol or larger will dissolve in an organic solvent, but with water, it takes a little bit more effort. Now, luckily for people who like to enjoy alcoholic beverages, it dissolves completely in water, right? Otherwise, you would have to, consume it as a powder, which they now make powdered ethanol. I don't know if it's ever been able to sell, but for a while, they were marketing this powdered ethanol that you could take with you if you went on backpacking trips, right? Because it's a lot lighter and you can just sprinkle it in a little bit of water and there you go. I think that it's particularly dangerous because you can make very, very high proof, high percent alcohol if you're not careful. But for a while, that was a thing. And if you think about things like multivitamins, certain vitamins are fat soluble, certain vitamins are water soluble, right? And why is that? Because some of the vitamins are polar or more polar and are going to dissolve in water. And other vitamins are have these non-polar ends that are going to make them more likely to form solution with fat, which is also non-polar, right? That's why oil doesn't mix with water. Okay. And so that's why if you're taking vitamins, it's okay to take quite a bit of water soluble vitamins because then you just excrete them out. But if you're taking fat soluble vitamins, you got to be careful that you don't overdo it. The more similar the intermolecular attractions, the more likely one substance is to be soluble in another substance, right? So again, if you take these polar attractions like dipole-dipole interactions, and those are what are keeping the solute together, and you put them in a solution that also has dipole-dipole interactions, they're going to blend more readily, right? Just because, again, they're more similar and like dissolves like.
I have a quick question.
Yeah.
I was just wondering why it's like dissolves like, and it's not just like the stronger forces that take over. If that makes sense.
Yeah. Well, so if the stronger forces, if it takes too much energy to break those strong forces, then it's not going to happen. Okay. But in most cases, if it takes a little bit of energy to break, let's say, a strong ionic attraction, then because these forces want to be similar, so forces in water, they're perfectly fine as let's take water as the solvent again. Those forces are happy, they're stable as they are. If you throw in a non-polar substance, solute, that has its own attractions and forces that are different, it's going to cause trouble. It's going to make the water unhappy. Okay. And so the way around that is if there's not sufficient energy put into it, it'll just separate it out, right? And the non-polar stuff will rise to the top or float to the bottom, depending on its buoyancy and its density. And now you don't have a solution, right? But in order for something to have a solution, it has to be homogeneous. It has to blend in, okay? And so because the attractions between two like substances are the same or very similar, it allows them to blend in without any kind of instability or to be anthropomorphic. It doesn't cause the water to be angered or agitated. Does that make sense?
Yeah, I think so. Thank you.
So let's take glucose, for example, right? Glucose does hydrogen bonding. Water does hydrogen bonding. Glucose by itself is a solid, right? But because both of them have hydrogen bonds, when you put glucose in water, they blend and they form solution, and the glucose dissolves to a certain degree, right? Until it reaches saturation. But cyclohexane, that's an organic solvent that does not have hydrogen bonding. Okay, it does, because if you look at this molecule here, where's my drawing? Right here. What's it missing? It's missing oxygen. It's missing nitrogen. It's missing fluorine, right? So it can't do any hydrogen bonding. And therefore, the glucose is not really going to as readily dissolve in that cyclohexane. Okay, and so the question is, well, what if we got rid of some of those OH groups, those hydroxyl groups on sugar, and replace them with methyl groups? What's a methyl group? It's a CH3. How would that affect the solubility in water? What do you think? Would that make it more or less soluble?
Would it be more soluble because it could do hydrogen bonding?
Well, no, because it's the hydroxyl groups that allow the hydrogen bonding. That's why the cyclohexane doesn't dissolve glucose, doesn't mix well with water, because it doesn't have the oxygens. Okay, so if you took those oxygens off of that sugar molecule and replaced them with just hydrocarbons, now it's not going to be able to readily dissolve. And I mean, it still could, right? Because as we said, alcohols can dissolve in water, and they have OH, but they have OH groups, right? So if you get rid of all those OH groups, now you just have essentially a hydrocarbon molecule. It's similar to cyclohexane. And so it's not going to form those hydrogen bonds. It's not going to dissolve as readily, but it will dissolve in a cyclohexane solvent. Okay. So these hydroxyl groups are important in terms of water solubility. Now, what do you think, going back to the vitamins, what do you think a water soluble molecule is going to have more or less? You think is it going to have more hydroxyl groups or less hydroxyl groups? Let's put it that way. Remember, sugar, glucose is highly soluble in water, and it has a lot of hydroxyl groups. So if a vitamin is going to be soluble in water, it's going to have a lot of hydroxyl groups to form those hydrogen bonds, because like dissolves like. Okay. Oh, let me clear that circle there. Now, how does a temperature affect solubility? Well, usually the solubility of solid solutes in liquid solvents are going to increase as temperature rises, right? So again, going back to our example of salt water, if you put salt in cold water, it'll dissolve if you haven't reached the saturation point, right? But it won't dissolve as quickly. And then also, as you raise the temperature, you raise the solubility. So you can dissolve more salt, more sodium chloride in the same amount. You can dissolve more in the same amount of water at a higher temperature, right? So looking at this graph, solubility, grams of solute per 100 grams of water. As you increase the temperature, for most of these, you increase the solubility to a certain degree. So as temperature goes up, solubility goes up, right? The opposite is true with gases, though. That's with solids, okay? As we decrease, or as we increase the temperature, we decrease solubility, okay? And that's why, that's why things like soda, right? If you open up your soda and it's a warm soda, it's just going to fizz out and get flat pretty quickly, right? But if it's a cold soda, it's going to more likely have that gas in solution for longer, right? Warm lakes have less oxygen. Yeah.
Sorry, didn't mean to interrupt there, but does the temperature of the COVID vaccine and how it has to be kept extremely cool have to do anything with this? With the solids, at least, because I know gases, it's not.
Yeah, no, the temperature is that it's an mRNA vaccine, and RNA is incredibly unstable. And so that's why when forensic scientists go to crime scenes, they collect DNA. They don't collect RNA. I'm spewing RNA all over my laptop right now. As you talk, you shed it everywhere, but it doesn't last very long. It gets degraded by enzymes. It's not very stable. And so that's why it has to be stored at that really low temperature of minus 80, because, or even colder, I think, because that is what's keeping that mRNA from degrading.
Okay.
Is there anything other than cold temperatures that could keep the mRNA stable? I mean, like,
that's a good question. I think that the Moderna vaccine doesn't have to be as cold. And certainly if you package that RNA in like a fat droplet. Remember, we talked about our first journal club, which, by the way, journal club is Wednesday for section 1, tomorrow, Thursday for section 2. We're going to talk about Watson and Crick and Rosalind Franklin. But if you remember the first one we talked about, the first journal club, we were talking about stability of of these prebiotic molecules, right? And so, yes, if you could package that RNA in some way that it was free of enzyme degradation, you could probably not have it that cold. But I think room temperature would not be good. Just RNA, it's in general, does not do well at room temperature. And so I think you might be able to get around that extreme cold, but it's probably a good idea to keep it cold.
Yeah. I was just remembering learning about something about skincare with vitamin C, and how a lot of skincare products that have vitamin C also have ferulic acid in it, because the acid helps keep the vitamin C molecule stable, and they're also packaged in containers that are not clear, because the light is what makes the vitamin C unstable and break apart, and then it doesn't help with anything.
Yeah, with the thing about RNA, especially messenger RNA, is that is what leads to gene expression, right? So if you need to start producing a certain protein, like the body detects some external stimulus, and now it needs to start producing some biomolecule, it's going to go to the DNA in the nucleus, and it's going to unravel it, and it's going to then transcribe a corresponding RNA segment, the messenger RNA. And that messenger RNA is then going to leave the nucleus and find the ribosome in the cytoplasm, and the ribosome is going to start translating that into a protein, right? But you don't want to constitutively express that protein indefinitely. At some point, you want to say, okay, we've made enough of that. We're done. And because RNA is so unstable, that's a good thing. You don't want a bunch of RNA hanging around in the cytoplasm indefinitely, because you don't want it to continue to be translated into proteins, right? You want it to go, it's like, I don't know if you think about like Mission Impossible, right? This message will self-destruct in whatever, 10 seconds, right? You don't want that message hanging around longer than it is there to do its job. So RNA is inherently unstable for a good reason. And it's beyond just simply protecting it from UV light and stuff like that. But yeah, definitely different molecules have their different levels of stability, whether it's temperature or environmental exposure to enzymes or the sun, radiation, that kind of a thing. Good questions, guys. But yes, so gas is less soluble as temperature goes up. That's why when water gets too warm, it loses significant oxygen content, which is bad for the aquatic life, right? May be good for things like algae, right? Which is why in the Tahoe Keys, they've cut all those channels in, and the water's warmer because it's not as deep, and so you get a lot of muck and algae and stuff like that, but it's also less oxygenated. So and certainly people could argue that cold water tastes differently than room temperature water, right? Why do we like our water cold? Well, because it has different gases that confer different flavors. And we talk about that. If we do our coffee thing, we'll talk about that as well. So, again, getting back to this concept of gases forming in solution, right? As I said, gases solubility increase as temperature decreases. Also, the solubility of gases increases as mass increases. And if you think about it, it's because this is all related to pressure. Okay. Remember vaporization, right? If you have vapor, gas, right, over a liquid, and you compress that gas, you increase the pressure, you're going to drive more of that gas into solution, right? So let's say we have our carbonated water in Tahoe, and it's the same exact temperature as, it just happens to be the same temperature as it is down in the Bay Area. What is going to stay carbonated longer? Which area? In the Bay or in Tahoe? Based on what we know about pressure. Bay, right? Yeah. There's more pressure. There's more atmospheric pressure in the Bay Area. Okay. And we relate all of this using Henry's law. So now comes the math, guys. I know you were anxiously awaiting some math, and here it is, okay? We can say that S, or sometimes you'll see it as C, but S and C are used interchangeably. S or C of the gas, that's the solubility of the gas, is equal to Kp. K is Henry's law constant for the particular gas that is going into the solvent, right? So it'll change depending on what the gas is, times the pressure, okay? So solubility equals Henry's law constant times pressure. Pressure is the partial pressure of that gas above the liquid, okay? Hasn't gone into the liquid yet. So we can determine how much gas, and it's an ideal gas, okay? So remember ideal gas law. So we have to use certain assumptions behind the behavior of this gas in order to apply it to Henry's law, but we get pretty close. We can define how much is going to dissolve in a certain volume of liquid solvent, okay, based on what is given to us in terms of the pressure. Or, you know, if we're given the pressure and the constant, we can determine the solubility, right? Or the solubility and the pressure, we can determine the constant. Okay, so that's the relationship of these. And so here's our problem, okay? At 20 degrees Celsius, the concentration of dissolved oxygen in water exposed to gaseous oxygen at a partial pressure of 101.3 kilopascals, which is equal to 760 torr, right, is 1.38 times 10 to the negative 3 moles per liter. Okay, that's the concentration. Use Henry's law to determine the solubility of oxygen when we change the partial pressure to 20.7 kilopascals or 155 torr. Okay, which is the approximate pressure of oxygen in the Earth's atmosphere. So how do we go about doing this problem? Well, we got to use C equals Kp. And then we got to determine what are we solving for, okay? We know that we're given 1.38 times 10 to the negative 3 moles per liter. So we have that. That is going to be the concentration, right? That's C. And we have our partial pressure at 101.3 kilopascals, okay? So we can use those two things to find K, Henry's law constant, for oxygen. Once we have that, then we can see what happens when we change the pressure. Okay, does that make sense? Let me write it on the board, move things around, see if you guys can work this out, okay?
So if K is the constant, is it always the same or does it depend on what the substance is?
It depends on the substance. So it's going to be the substance, it's going to be the K for a particular substance. In this case, we're looking for the K for oxygen. So let me get my lights going the right way. Here we go. So what do we have? At 20 degrees Celsius, that's a little bit of a, that's the red herring in there, right? They're just throwing in more information. I mean, it's kind of a red herring, it's saying that it's, we're at, you know, STP essentially, okay? The concentration is 1.38 times 10 to the negative 3 moles per liter, right? That is our C gas. And then they say that the partial pressure, so the P gas, is 101.3 kilopascal. Or if you want to do torr, okay? But whichever. And so in this case, we got to find out what K is. So find out what K is, and then we have that constant, and we can use that over here to say, okay, well, concentration stays the same, but we've changed the pressure to 20.7 kilopascal. Did anyone get K?
I got 1.362 times 10 to the negative 5.
I'll confirm that.
That's what I got too.
1.362 times 10 to the negative 5?
Yeah.
Okay. So now that we have this for our K, we just plug it in with our different pressure. So to get
What are the units for K, and does it matter?
no. I mean, I guess the units would be, so it would be moles per liter per kilopascals, right? Moles per liter per kilopascal. And let's see if that matters. So now what are they saying? What's the question? The question is determine solubility, right? When we change the pressure. So now we know what the K is. We want to see what this C is once we change P. So we say C is equal to 1.362 times 10 to the negative fifth moles per liter per kilopascal times 20.7 kilopascal. What's that?
(2.82 times 10 to the negative 4).
And what cancels? Kilopascals. And we get our units of moles per liter again. Okay. Everybody else get that answer?
Yep.
Yeah.
All right.
Sorry, you were just solving for C, is that right? So C didn't just translate from the first part to the second part?
No, we're solving for C. Yes, because it's saying the concentration of oxygen is 1.38 times 10 to the negative third at this pressure, 101.3 kilopascals. And so they're saying, what is the concentration when we change that pressure, right? Because remember, solubility is directly proportional to pressure. So they give us the solubility. And again, it's, vocabulary here, right? So what they're saying is, oh, I got rid of my annotation. Sorry, guys. Hold on. Hold on. I'll move this up a little bit. Otherwise, it's in my way. Okay. So they're saying the concentration of dissolved oxygen is 1.38. That is solubility, right? Determine the solubility of oxygen. That is going to be, again, essentially concentration. So that's why it's changing for this problem. Okay. There we go. Try this one, and then we will take a break and do some coffee stuff. So how many moles in carbon dioxide are dissolved in a 2.0 liter bottle if our constant is 3.1 moles per liter times atmospheres? And there's a pressure of 4.4 atmospheres in the bottle. So again, this is another way to word it, but you guys gotta think about what is what, okay? What are they asking for? They're asking for how many moles in a certain amount of liters. How many moles per liter? What is our moles per liter? Our concentration. So they want to know the concentration. They give you the K. They give you what else?
The P.
P, 4.0. And from there, you can do the rest. not atom, atmosphere. Okay, and what's that?
12.4.
Okay, but that's moles per liter. They want to know moles per 2 liters, right? Because it says how many moles of CO2 are dissolved in a 2.0 liter bottle. So what do we do?
Multiply by 2.
Easy peasy, and we get 24 moles. Okay. So not too bad, right? Not too bad. I think I just have one more problem. Let's soldier on for the last problem and then take a break. Sorry, guys. There's just one more on the slide deck. Might as well do it because we're having so much fun. Oops. Okay. Here. What is the pressure of carbon dioxide that is required to keep it in concentration in a bottle of club soda at 0.12 moles per liter at 25 C? Well, what they don't give you is the K, but I've given you the K. So the K for CO2 is 3.4 times 10 to the negative 2. You have that. You have your concentration at 0.12 moles per liter, or the molality, the molar, and molarity. And so just plug and chug, right? What do we got for that? Oh, CP equals K PG. We want to find pressure. We just say that P, pressure of the gas, is equal to the solubility of the gas over K. In this case, it's 0.12 over 3.4 10 to the negative 2. This is in atmospheres. So what's that?
3.53 atmospheres.
Okay. 3.53.
Yes.
Okay. That's the pressure required to keep the concentration in that bottle.
So the temperature didn't even play into it, right?
No. Now remember, temperature, when you increase the temperature, you decrease the solubility. And so they're just telling us this temperature so that we know that the temperature isn't really changing, it's staying constant. And it happens to be a room temperature, 25 Celsius. It happens to be kind of a room temperature. So it's standard for standard temperature pressure, STP values.
So if it was a different temperature, would we have to add that into our calculation then?
Yeah, we would have to factor that in if it was particularly an extreme temperature, right? So remember, that, oops. If we looked at that graph again, for, well, carbon dioxide's not on here, but oxygen, for instance, if you increase the temperature, you decrease the solubility. And so Henry's law only works at STP. Okay, let's take, how long of a break do you guys want? We've got some time, right? It's only 2:12. So you guys want a 10-minute break or a 5-minute break? I'm giving you the option.
You like it round, so how about 13 gives us 25 or 8 gives us 20?
I like that. Let's do 13-minute break. Sound good? Okay.
I like it.
So we'll meet back at 2:25. All right. Can everybody hear me okay? Yeah, okay. So what I want to do now is focus what we've learned a little bit into what I really enjoy is coffee. And again, this is caffeine and coffee is a solution. Yeah. And the solution that we make is dependent on all different types of factors, okay? One factor is going to be the temperature, right? As we know, temperature affects the rate of reactions. Temperature also affects gas exchange, right? The size of the actual grinds, the coffee grinds, makes a big difference in terms of the taste, in terms of the extraction, right? Because coffee really is just, from a chemistry perspective, an extraction. We're taking fruit, which is why coffee, if anyone asks me what my favorite fruit is, I say coffee, because coffee is not really a bean, right? It looks like a bean, but it's a berry. Now, we're extracting all these different flavors from that berry. And to do that, you have to have different parameters to get different flavors, right? So temperature is one, grind size is one. Of course, your ratio of coffee to water is going to be a contributing factor. The less coffee you have to water, the weaker it's going to be. And then also the type of roast will contribute. And I have two different types of beans. So if you're coffee drinkers and you like to buy your beans whole, you might know that some beans are really shiny on the outside. And I don't know if I can really do this.
Greasy beans.
Greasy beans, yes. I don't know if you can see that shimmer, but yeah, it's probably not gonna show through. But these aren't the same. This one is shiny, greasy. This one is not. And for the longest time, I thought that the ones that weren't greasy were just over roasted. And it just like evaporated all the oils. But then I talked to my good friend Jared. I don't know if you guys have heard of Refuge here, but it's a local coffee company. I met Jared, the owner, at Blue Granite Climbing Gym because he used to have a little shop there. Yeah. And he was telling me that actually when you over roast the beans, you roast them so long that the oils inside start leaching out, right? And so when you see these greasy beans, it's usually from beans that have been roasted in bulk and just kind of just roasted the heck out of them, okay? So I prefer to get the beans that are more like artisan roasted, but those differences are going to really contribute to the overall flavor of the coffee, because your roasting is what translates all of the sugars and proteins in that initial berry into the 800 plus flavor molecules that are then derived. So that's why we take that green berry and we roast it into this black thing, because it changes the molecules in that berry. And then when we extract those molecules out, that's what gives the flavor. Okay.
Wait, is beans a grape?
No. Beans are a legume. But so so those are the different components. And I am by no means an expert here. I do know that Alex was a barista. So feel free to hop in if I say anything wrong or if I miss anything. But what I wanted to go through is my technique for what I think is a really good cup of coffee. And I will preface this by saying that I went through this process for my wife, and I made her a cup of coffee, and she's like, oh, it almost like it tastes sweet. And to me, that was the ultimate compliment, because coffee, if it's done right, should give you these actual, not like candy sweet, but different sweet flavors. Problem is, the way we make coffee generally extracts out a bunch of the bitter compounds with it. And so it masks all the really, in my opinion, wonderful flavors, okay? And again, a lot of this comes down to preference. Water quality is also going to affect things. So if you have really soft water, so not much minerals, especially like bicarbonate in there, then you're going to pull out a lot of acids from those beans, and they're not going to get neutralized by the bicarbonate. And so it's going to have an acidic, kind of a sour taste to it, okay? Now, if you have a lot of bicarbonate, then it's going to neutralize some of those acids and get rid of the sour, but it's going to give it kind of a chalky aftertaste, because think of bicarbonate as kind of like an antacid, right? And antacids, Tums and stuff are really chalky. So it's good to have a little bit of mineral in your water. You know, you don't want to get purified water per se. So that's going to make a big difference as well. And so I hear sweet is good, over extracted is bitter, under extracted is sour. Yes, so if you under extract, and when we extract, coffee has about a 30% solubility, okay? And what people usually try to aim for is between 18 to, I think, 22%, okay? And if you get an insufficient solubility or insufficient extraction, it's going to have, yes, this sour taste, because you're getting most of the acids coming out. And what contributes to that? The grind size. Now, I don't have a fancy burr grinder, which gives you a nice uniform grind. All I have is a blade grinder, which is not great because it gives you a heterogeneous size of grinds, right? You get some big ones, you get some really powdery ones, and then you get some in between, okay? And so really what we want to aim for is a uniform grind size. And so to do that, I use my pestle and mortar, okay? That way I can control exactly how coarse or how fine my coffee is. And like Alex said in the chat, if it's too coarse, it's going to be weak and it's going to be kind of on that sour side. If it's too fine, it's going to be bitter, right? Because you're extracting out more of those bitter flavors. You're also getting some of like the silt, that sediment at the bottom too, okay? So I only do this for my first cup of coffee in the morning because it is kind of labor intensive. And then after that, I do my regular process and I really can notice the difference. Another thing that I mentioned is your ratio of coffee beans to water. Now, at least from what I've read, a good starting point is about 28 grams of beans to 400 mils of water. And then you adjust from there based on the type of bean you have, the grind size, your own preferences. I've been doing around 40 grams per 400 mils. And so I use my food scale.
Mm-hmm. That he got from Christmas.
Yes, I bought myself a food scale for Christmas because that's the only way I get presents for Christmas. But now you're going to tare it. What does tearing do?
It makes the bowl like 0.
Yes. So we've tared our weigh boat, if you will, and we're going to measure out 40 grams.
40.
Perfect. And then Bennett usually likes to do the grinding. I let him go until he gets tired and then I finish it off. So I'm going to let him start to grind. And while he's doing that, I'll tell you that I've experimented with hand grinding and then also using my blade grinder. And there's definitely a difference in taste. So this seems like a lot of pretentious effort. And my wife usually rolls her eyes when she comes in the kitchen and sees this, but it makes a difference. And if you're a coffee snob, which I am not, I'll drink any coffee because I'm a fiend. But if you're a coffee snob, then this is the way to go, all right? Also, this is not essential, but this is called a separatory funnel. So if you guys take organic chemistry next year, you'll probably use this a lot, assuming we have face-to-face labs. But essentially, we would also use this if we do a titration for our acid-base lab that we would do later on this quarter. And essentially what you have is, this is called a stopcock, and you turn this, keep grinding, and that opens up the flow, and you can adjust the rate. So you can have it go drop by drop, or a bigger stream, or a narrower stream. And the reason I like this is, one, because it brings me back into the lab. This is not used. I bought it, at least, I think I bought it brand new on Amazon. So it probably doesn't have any heinous chemicals that have gone through this in a previous chemistry lab, I hope. But what it allows, what? Where you going?
And you have to, when it's going down, you have to have the cap off so it can have airflow.
Oh yes, airflow. Yeah, you don't want to leave the cap on because then it will stop flowing. But anyway, the reason I got this is because when we start pouring over the coffee grinds, you want a nice thin stream of water, okay? Because if you just pour it all on, you don't get a nice bloom. And the bloom is important because we want the coffee grinds to kind of rise up and release the carbon dioxide that is a byproduct of the roasting, okay? And what this allows me to do is to dial in a very specific stream so that I can get a wonderful bloom, and I don't have to stay. I can, like usually I'm doing this and the kids are asking for a bagel or milk or whatever. And so I got to like walk away and multitask, and I can just leave it under my separatory funnel. How's it going? Okay, let me finish this off. I'm going to finish this part off, and then I'll show you kind of what it looks like. Hopefully you can see. I have developed an appreciation for Native Americans that had to do this for to grind their cornmeal and stuff all day, because this is actually a pretty good arm workout. It's very tiring. And side note, if you guys have ever gone out past LTCC's campus to the river, there's a rock there, and I can't think of the name of I think it's called, maybe it's Indian rock, Native American rock, but it's a big giant rock in this field, and it has all these holes in there that are presumed to be where the Native Americans were grinding their corn and stuff. So it's a bit of an archaeological site. Does anybody know what I'm talking about?
No.
Not you. No.
Yeah, I don't think I've ever seen it in person, but I've seen pictures of it.
Yeah, so it's neat. But yeah, this is a little bit of effort, and again, this is why I just do this with my first cup of coffee.
Have you ever experimented with doing a combination of using the blade grind and the mortar and pestle? Because I would think maybe you could get it started with the blade grinder and then do the rest with the mortar and pestle.
I have tried that, but really I find that what it does is the blade grinder gets these, it's even initially it'll get these small pieces in there, and then I've gone and tried to break out some of the bigger ones, but I still get a lot of these ultra fine particles that that it just gives me a less desirable overall taste. And I mean, again, it's subjective, right? I mean, I think it's still good if you do the grinder, but it's not as good. And this is about brewing the perfect cup of coffee.
That method would be really effective if you were brewing espresso, because you want a super fine grind on that. But for the pour over, you're going to want it more coarse.
Yeah. So
Kind of like that.
let's see if you can see.
That smells wonderful.
Oh, doesn't it? So, yeah, it's not really showing up, but the idea is that you get a nice consistent grind. There's a few pieces in here that are bigger than others, but on the whole, it's much better than that really fine stuff that Alex said is more espresso style grind. So now he's going to do the second part. Okay. And during this time, I wanted to talk about how does caffeine work? Does anybody know the mechanism of my favorite molecule?
I was just,
I have a very vague idea of it because I did learn about it at one point, but I've forgotten a lot. But I'm pretty sure it's that like molecule blocks the receptor for the hormone that makes you feel tired.
Yeah, so not particularly a hormone, but this molecule is similar enough to adenosine. Adenosine, you guys might know, is what makes up ATP, so adenosine triphosphate. And that is our energy producing molecule. It's what when we go cellular respiration, right? We breathe in oxygen and it goes through these different steps to eventually yield ATP. Now, when your brain is thinking a lot, like in chemistry class, you are exhausting a lot of ATP in your neurons. And so what happens is you get byproducts. The ATP breaks down, it loses the phosphate, becomes AMP or ADP, adenosine diphosphate. And then even some of the adenosine will pop off. When the adenosine is free in your brain, it starts to bind to specific adenosine receptors. And when enough receptors have been bound, it tells you that you're tired. It downregulates things like dopamine, okay? So it's a neurotransmitter. Now caffeine, because it's similar enough in structure to adenosine, it will also bind those receptors. So when you go to sleep at night, you flush off all the adenosine off of those receptors. And then you wake up and you feel refreshed, right? You pop out of bed like a piece of toast and you're ready to take on the day. And then you drink that coffee and the caffeine binds to those receptors. And so you don't get that cue that, okay, now I'm awake, but now I'm starting to kind of calm down a little bit. You still have that alertness. Now the caffeine binding to it also is going to lead to an upregulation of dopamine, which is interesting. And that's what gives you kind of that, you know, okay, yeah, somewhat euphoric feeling. Now, because the caffeine is similar but not exact, it doesn't activate the adenosine molecule, receptor. It just binds to it.
Do you press and hold to turn it off?
Yes. So what happens is that it's competitive inhibition. All it does is it just doesn't let the adenosine get here. And so your brain after a while says, I'm not binding adenosine properly. I'm just going to make some more receptors. And so your brain cells start sprouting out more adenosine receptors. And now you have caffeine tolerance. So that initial cup of coffee that made you nice and alert is not going to have that same effect. Hold on. I'm going to lose my train of thought. Now, if you drink coffee chronically like I do, you have so many adenosine receptors that now you're below baseline of alertness. So you drink coffee and you do that just to get you to the point where you would be if you didn't drink coffee to begin with. So it becomes a vicious cycle and becomes kind of pointless. So if you only drink coffee, say once a week on the weekends, you'd have a much greater effect. You'd start pruning off all of those receptors and you'd be back in that nice, alert, concentrated concentration phase that caffeine is supposed to elicit.
Do you know why many like doctors and therapists recommend to people who have anxiety to not drink caffeine?
Yes, because caffeine, the adenosine receptors aren't just in your neurons, they're in your heart, they're in your kidneys. So when you're blocking those adenosine receptors, it's telling your kidneys that you need to pee because it's not binding adenosine. It tells it to kind of slow back. It also tells your heart that it needs to pump more because the adenosine is competing with the adenosine that keeps it at a nice rate. So with anxiety, a lot of times you have an increased heart rate, right? You feel like, now if you then add caffeine on top of that, that can have a synergistic effect and make your heart rate even worse. It's certainly not going to make the anxiety feel better. And that's why if you do drink too much coffee and you aren't desensitized to it like I am, you can get jittery if you drink too much, because then it will start affecting the adenosine binding to your heart.
And also, I drink kombucha in the morning.
Yes,
If
he
we
drinks
have-
kombucha,
If we have it.
but I don't let him drink it in the evening because kombucha has a little bit of caffeine because I make it with black tea, but it's a very minuscule amount. So I don't think I'm stunting his growth. But that in mind, when I was a little kid, my parents gave me instant coffee, which is terrible, right? You should never give anyone instant coffee. It tastes disgusting.
What's instant coffee?
You don't even want to know. It's that bad. And so that shaped my expectations of coffee until I was in college and then met friends who actually drank real brewed coffee. And then my life was changed from there, right? So, all right, we are at a point now where the beans are finely ground and I put them in. This is a Chemex. It was designed by a chemist and it's made out of borosilicate and it's supposed to be shaped optimally. It's got this really fancy filter that doesn't have any types of extra chemicals that will add to the flavor of the coffee. So I don't know. I use it again because I kind of nerd out about this stuff, but it's not essential, I don't think.
And you probably have seen some pictures that I took of the big bloom.
Oh, I haven't showed them any pictures of my big bloom, but I can if you want, if it doesn't show up very well here. Now, what I'm going to do is, because we've been learning about heat transfer, right, and thermochemistry, I'm going to heat up my water so that I kind of prime the cup so that it's hot, because we want to maintain as much thermal energy as we possibly can, because
He likes it hot.
Because what did we say about temperature and gases? All of coffee really is what you smell, a little bit of what you taste, but mostly what you smell. And so that has to be vapors coming out. And the higher the temperature, what do we know about the solubility of gas? It goes down.
The solubility.
Right? So there's going to be more of that aroma coming out the higher the temperature is. That's why if you get a big old venti coffee from Starbucks and it takes a little while, you get down to the last third and it's not really hot and it just tastes crappy. That's why, okay? Now, so I'm microwaving, the water's ready. What I'm going to do is I'm going to pour some of this water into my Chemex to get that primed with heat as well. And then I'm going to pour just a little bit on the top of the grinds, okay?
Yeah.
Just enough to get what's called a bloom. And if you have fresh roasted coffee, you should get a nice bloom. I don't know if you can see that. There should be lots of nice bubbles and it should kind of float upward, just like a bloom, like what you think of as a bloom, like a flower. And that's indicative of freshness because all of the carbon dioxide hasn't leached out, right? Over time, the carbon dioxide will come out and so will a lot of the other flavors that we enjoy. And so we let that bloom for about a minute or so. And I usually use my microwave as a timer for the water. And then we're ready to go. And it's 2:50, so if any of you have to go right now, by all means, you're free to go. Class is over. I'm just about done. So if you want to hang on for a few more minutes, we can see what the final product is, okay?
Here's some pictures that I took of the game.
Yeah, so Bennett's my helper in all kinds of different things.
Like
But
snow
he really-
plowing.
Yes, he snow plows with me. He does lots of things.
How old are you, Bennett?
I just turned 6 on December 20th.
Now, one important thing to do,
Oh, happy birthday.
make sure your stopcock is closed. Because I poured it before, the water in there, and my stopcock was open, right?
I didn't put it for
Now we are at a temperature of about 80, which is not particularly ideal, but that's about all that I can get with this apparatus. So I'm going to let the water slowly come out. I don't know if you can see that or not. Let's see here. Oh, it's just a little bit of a trickle. There's the picture of the bloom. Yep. Okay. Thanks, Bennett.
Okay.
And I'm just going to let it again kind of continue to bloom a little bit. You'll see these bubbles that are released. That again is the CO2. We want to get that out of there and let it slowly trickle in. And then after a while, because I don't want too much thermal energy to escape into the surroundings, then I'll crank it up a little bit more. But again, it's nice because I can walk away. I can get my cup of coffee or my coffee mug that has the water in it. And it's just doing its thing, right? Okay, now that we've got that bloom that's back, now I'm going to start swirling around to start getting water on all of the grounds or the grind. And
Kind of like that.
once I do that, it's going to look even more bubbly. So let's see if we can see that. See lots of bubbles coming out. And
Also, this is what it looks like when it's like water. That's what it looks like when it's
now, the reason coffee is so popular is definitely because of the caffeine, right? But the best thing about coffee really is the other stuff, right? And particularly, coffee has a lot of antioxidants, polyphenols. And one of the most important ones is called, oh, you taking a video?
I was taking a picture.
Okay. Chlorogenic acid, okay?
I was taking a picture when it was water.
And this is a lot of, okay, so now it's coming out. This particular molecule, it's a polyphenol, and it's been shown to interact and stop the process, one of the processes that's linked to Parkinson's disease. And I can tell you all about that if there's time. But essentially, if I drink enough coffee, I might be able to stave off dementia. And with 3 boys, I need all the coffee I can get, I think, to prevent that. It also has protective measures against things like prostate cancer. And then again, just generally sopping up all of the free radicals that, you know, bombard our molecules on a daily basis. Okay, so look here. So it's all gone through. I usually give it kind of a squeeze here. And there is our coffee. And I'm going to pour out the hot water here. I'm going to pour this in here. And look at that. And now, yeah, that's good. That's good stuff. So cheers, everyone. It is almost 3 o'clock, but that's not too late. I should be okay. Oh, I see see Miranda has her cup. I see Matt. A couple of you guys have some coffee or something else in there, maybe decaf. But cheers. And yeah, you're free to go now. If you want to hang on for a couple of minutes, we can talk coffee. I'm here. So let's chat or feel free to go.
What was the temperature of the water when you added it for the bloom and the titration?
So the temperature straight out of the kettle, probably a little bit less than 100 C, because I boil it in that kettle. And by the time you transfer it, it gets between 80 to 90 C. 90 is ambitious. If I can get it that high, then I'm doing well. But yeah.
And what was that like filter that you use? What kind of filter is that you put in the Chemex?
Yeah. So it's a Chemex filter. So it looks like this. And all you do is you pull out a filter, and it's folded into quarters. And you just take one side. Sorry, I could have gone through that. And you open it up like that. And I pre-wet it, and then I dump it out, and then I just stick it in the Chemex like this and put my grinds in there.
Do you notice a papery taste with the unbleached ones?
No. And well, honestly, I haven't done this whole process using the bleached ones. I've only used this kind of filter, so I can't really say what it tastes like if I used a different one, but that's a good question. These particular filters are supposed to be, like I had said, pretty free of extra chemicals that can leach into the coffee. And so it's not supposed to alter the flavor. But again, not being able to compare it to anything, I'm not quite sure.
I want to like the unbleached ones more than I do, but I feel like they just always make it taste kind of papery. I don't even know if it tastes papery or if it just smells papery, and I just like can't get that out of my nose.
Yeah, I mean, like I said, most of the coffee flavor comes from what we're smelling, right? So it could be that you definitely get that kind of the cellulose and stuff coming out of that paper, and then you're smelling that, and that's going to change the flavor. Yes. Have a good one. Thanks for sticking around. Now, we might continue this. If there's anything I missed, Alex, that you want to talk about or let me know about, if I misspoke or something, maybe we'll have another Cafe Franz session later on. We can certainly talk about coffee when we get into things like the Arrhenius equation, and definitely when we get into entropy. And also, if I were to add creamer to this, it should disperse throughout the entire solution, because that's what things do. The universe is constantly changing and going toward disorder, right? And so we might be able to bring this up in different contexts throughout the quarter, but if not, this is my process, and I hope you enjoyed it. And this is my side.
With like just a typical coffee maker, is the reason why that coffee is bitter because like the water's too hot, or it just floods the filter, or what's the reason why a typical coffee maker makes bitter coffee?
Well, I think it's potentially two reasons. One is how you grind it, right? So most people either
Hand grind it?
No, most people don't hand grind it. Most people are going to either buy it pre-ground, which means it's already lost a lot of its flavors because it was ground who knows how long ago. Or they use a grinder like mine, and you get all those different sized grind, particles. And then with the coffee pot, oftentimes you don't get that initial bloom. Sometimes it just kind of just sprays all over it, and so you're not releasing some of the carbon dioxide in there and allowing the extraction of some of the other better flavors that we like. And maybe Alex, do you have anything to add to that?
There's just such a lack of control, like you were saying, with grind size, whether you buy it pre-ground or you use a blade grinder. Most people that make their coffees at home, or even businesses that aren't good coffee shops, aren't going to weigh the beans. They're just going to use like however many tablespoons, which causes a lack of control. Definitely lacking the bloom would make the difference. I think a lot of it would just come down to, in order to make it properly, there are steps that you have to follow, and to just throw coffee into the coffee maker is just not as accurate as if you made it the way that he just did. And most of the time, if you screw up making a cup of coffee, the end result is going to be bitter.
Yeah, my mom is a big coffee drinker, and so I was kind of observing her process this morning, so that I could compare it to like today, if we got the chance to do it today. And like I know that like she just uses the scoop in there and does like 3 heaping scoops. And then when I was watching the coffee pot actually make it, you were right, it just kind of splutters the water out, and like it flooded the filter.
Mm-hmm. Yeah. And so, again, when we talk about brewing coffee, we're not really brewing it as much as we are extracting it. To brew it, when we brew stuff, you essentially put a bunch of stuff together and you let it kind of just sit, right? You brew beer, you can brew kombucha, right? I have a mother, right? And I put in water and it just sits together and it brews, right? You think of witch's brew, in the cauldron, right? Coffee, it shouldn't be considered a brew. At least I think it should be considered an extraction. And when we take it to this kind of level, which, like I said, it doesn't have, you can have most baristas will use more like a teapot that just has a little skinny nozzle at the end, spout, I guess is what it's called. And it does the same thing, right? But when you think of it as an extraction, it becomes a very different process than just putting, and I have a French press, I have an AeroPress, I have all these different things that can be used to make coffee, and it's like a backpacking French press kind of in a way. But the French press, French press is my least favorite, honestly, because you have to have kind of a coarse, you can't have it super fine, because then when you put the plunger down, if you're not familiar with the French press, right, you throw the grinds in here, you put in the water, you stir it around, and then you put the top on and you push this plunger down, and that kind of pushes the grinds down. So you don't want it super fine because it'll get through that mesh in there. And so again, what I end up with is just a gamish of a bunch of different grind sizes. Some are coarse, some are really fine. And then it tastes really bitter because there's no bloom involved. There's no releasing any of the CO2. And so you're pulling out everything without specific selection.
I didn't know that a French press, like I didn't know if it was supposed to be for coffee or tea, but I guessed that it was for tea, not coffee.
You could probably use it for tea as well.
I totally make loose leaf tea in mine because I broke my tea steeper. You can use them for both.
Yeah. So let's see. I don't know. Yeah. So this is typically what people will use for loose leaf tea, but yes,
Yep,
when that
that's
breaks,
what I use.
yeah, when that breaks, a French press would probably do it. Clearly, it does. So yeah,
Tea doesn't
Thank
have
you.
grounds, does it?
tea is ground up leaves and herbs and stuff. Yeah.
I feel like there has to be some way that we can make like an espresso AeroPress like pressure lecture. Like it should somehow factor into that stuff. That would be fun.
Yeah, absolutely. Maybe I'll think about that.
I was wondering if we could ever do like anything with cooking and molecular gastronomy.
Potentially, yeah. You know, so I kind of avoided that kind of stuff because I wasn't sure. I didn't want to exclude people that didn't have a fully functioning kitchen and all the cookware and stuff like that. But we could definitely do something like this. And if you have the stuff at home, you can follow along. And if not, you just follow along virtually. That would definitely be an option. I think that that stuff is really cool and fun to do. And AeroPress, they win all kinds of awards with their coffee. I think on the box it says the best latte I've ever had. So thinking about that and in terms of what's going on with the pressure on that would be interesting. And then certainly cooking chemistry is a really fun avenue. And I thought about that when we first started closing down campus. Like, can we just do some kitchen chemistry? And yeah, we could probably, let me think on that, Hannah and Alex. Let me think on those options, and maybe do one of those instead of an ICA. I don't know, you guys. I don't. Sure, there wouldn't be too many people that would argue against that, but yeah, I'll think about it. And if campus is, I don't know if any of you guys are taking Chem 103, but that'll be with me again. And if campus is still closed, then we might have to get more creative.
Thank you.
All right, guys. Well,
Thank you.
I will. I'll see you all Thursday. Remember that we have our journal club, so don't forget to read those papers and write your critique and turn it in before our discussion. Okay. And it's snowing out there pretty heavily, so for those of you in Tahoe, if you have to go out, please be careful. Okay. And have a good evening. We'll see you next time.
Bye.
Awesome. Thank you.